Okay, students, Assalamu alaikum. We are going to start our lecture today. So just to recap, what we have done is that in the very first lecture, we discussed about fluid. What is fluid mechanics in general? And what are the properties of the fluid? We discussed this in the second and third lecture. Okay? So today we are going to start with lecture week 4. Okay, and in this we are going to start with the first topic of fluid mechanics, which is actually fluid statics. So I told you the similarity of fluid mechanics with solid mechanics. You have been studying solid mechanics. You studied solid mechanics. The first part of the solid mechanics you studied as statics. Okay, so it was actually solid statics, which we call it just statics. Okay. And then after that, you studied dynamics, which was actually solid dynamics. Okay. And within solid dynamics, you studied kinematics, then kinetics. Okay. So the same pattern is going to be followed here for the case of fluid mechanics as well. So you're going to first study fluid statics, which will be followed by fluid dynamics. And within fluid dynamics, you're going to have fluid kinematics, and then you'll have fluid kinetics. The same pattern which you followed for the case of solids, we will also follow the same pattern in the case of fluids. The only thing is that in solids you are taking it as separate subjects. Okay, static was a different subject, dynamics was a different subject, although they both combine together in solid mechanics. Okay, but here we are taking it as a single subject, fluid mechanics. Okay. So initially we are going to start with the fluid statics. So conceptual knowledge, today we are going to discuss, we're going to describe pressure and pressure distribution. We're going to discuss about the gauge, absolute and vacuum pressure. We're going to list the steps used to derive the hydrostatic differential equation. Some of the procedural knowledge we are going to get, and a little applications as well we're going to discuss. Topics are the pressure variation with elevation, pressure measurement, hydrostatic forces on plane surfaces, hydrostatic forces on curved surfaces, buoyancy, hydrometer, stability of immersed bodies, stability of floating bodies. These are all the topics that actually cover the subject of fluid statics. So let's first discuss the most important thing in fluid mechanics, which is the pressure. Okay, so fluid statics is the study of fluids in which there is no relative motion between fluid particles. No velocity gradient in the fluid. So look, you have to understand one thing. When we're talking about fluid, there's always a little motion in fluid. But when we are saying fluid statics, that means we are talking about a specific fluid where there is no bulk motion. Now, bulk motion is something else. You can actually see the fluid moving in a specific direction. That is the bulk motion of fluid. So a river is flowing. There is a bulk motion of fluid. You can actually estimate where is the direction of the fluid. Okay. So you have water flowing somewhere on the ground. You can see where it is flowing. There is a specific direction associated with it. Okay. But if you go to if you go to a seaside and you find the ocean, okay, so the ocean is there. There is motion in the ocean, but there is no specific direction of that motion. It's all around haphazard. Okay. So when we are talking about fluid statics, we are dealing with the fluid where there is no specific directional motion. Motion is there, but directional motion is not there. Okay, so that is fluid statics. So fluid statics is the study of fluids in which there is no relative motion between fluid particles. So there won't be any relative motion between fluid particles. No velocity gradient in the fluid. Okay. Therefore, no shearing forces exist. Shearing forces exist if you have layers of fluids. If you have layers of fluids and these layers are moving in some direction, so there will be relative motion between the layers. And when you have the relative motion between the layers, So these layers will rub against each other. When the layers rub against each other, so there will be shearing forces. But if there is no relative motion, there won't be any shearing forces that would exist. Okay, so in fluid statics, shearing forces will not be there. So the viscous effects will be not applicable. So viscous effects comes when the fluid layers move against each other. So they have the resistance against each other, okay, that causes them to dissipate energy, okay, that causes the fluid to become thick, okay. So the thickness of the fluid cannot be visualized if the fluid is not in motion. So you have a jar full of water, you have a jar full of honey, but nothing is in motion, so you cannot judge which one is thick, which one is thin. The only point when you can judge whether one fluid is thicker than the other, when you pour the two fluids. So then there is the motion, and based on the motion, you can judge, okay, this fluid is thicker, this is thinner. This is more viscous, this is less viscous. Viscous effects are applicable, viscous effects are visible when there is a relative motion. Okay. So when there are no relative motion, no shearing forces, viscous effects are not applicable. They are present, but they are not visible. Okay. So in case of the fluid statics, no shearing forces exist, only normal forces exist. Now these normal forces in fluids are called the pressure forces. So pressure forces are basically the normal forces. What are the normal forces? You have studied it in statics or strength of material. The difference between the normal and the shear forces. The normal forces are the one which either tends to elongate or tends to compress. So if you have a fluid and there is a normal force tends to compress the fluid. Okay, so that is basically the normal forces, and this is what pressure is actually termed at in fluid statics. So pressure results from a normal compressive force. Pressure results from a normal compressive force acting on an area. Mathematically, P is del F over del area. Okay. The force is a normal, where del F is a normal force acting over the area del A. Pressure is a scalar quantity. Pressure is a scalar quantity. It has magnitude only and acts equally in all directions. So if there is something which is unidirectional or bidirectional, then we call it is vector quantity. Okay, if it is bidirectional, then it is a tensor quantity. So, but anyways, but if it is acting in all the directions, then actually it is not acting in any direction. So we consider it as a scalar quantity. It has magnitude but no direction, no specific direction, because it acts equally in all directions. Pressure is a scalar quantity. This is a point to remember. Okay, I can ask you in the exam, is pressure a vector quantity or a scalar quantity? Okay, force per area. Now let's talk about the unit of pressure. Since it is force per unit area, so unit of pressure will be Newton per meter square or Pascal. Pascal is basically Newton per meter square in SI units, or PSI, pound force per square inch, or PSF in the traditional units. Traditional means English units. Okay. Now this is something which you have already studied. Pressure, how do we define pressure? What's the unit of pressure? Pascal. What's the unit of pressure? Newton per meter square. But there is another way of defining it, and that is by the liquid column height. This is something new. This is also a unit of pressure, liquid column height. Okay, so in simple terms, okay, how do we define it? Let's say this is the surface. this is the surface over the pressure will be applied. Okay. If I have to apply a specific pressure over this surface, okay, what should be the height of liquid column? So if let's say if I have a liquid column, and this column is filled with liquid. Okay. So obviously if I hold this column in my hand will feel the pressure. Okay. So what should be the height of this column that will exert the same amount of pressure, the amount of pressure which I am actually talking about? Okay. So that's another unit of pressure. Okay. So suppose I say that 100 kilopascal. And suppose I know that if I take a liquid column of water, which is 5 meters in height, that 5 meter of liquid column of water is going to provide a pressure of 100 kilopascal. So either I can say 100 Pascal, or I can say 100 Newton per meter square, or I can say 5 meter of column height of water. They all mean the same thing then. So liquid column height is another unit of pressure. Okay. And it specifically means what? You have a column. The column is filled with the liquid, whatever the liquid we are discussing about. It could be mercury, it could be water, it could be alcohol, it could be any oil, whatever it is. So I have a column. That column is filled with that liquid. And what would be the height of that column so that it provides the same pressure, the pressure which we are talking about? So that's another way of defining the unit of pressure. And this way is something that you are studying it for the first time. And this way is going to be used a lot in this course. So this is also a unit of pressure. In fluid mechanics, this is also a unit of pressure. What is the height of the liquid column? A liquid column could be water. So sometimes we say like this. Okay, sometimes we say 0.2 meter of water column. 0.2 meter means we have a column of water, which is the height of the column of water is 0.2 meter. Okay, and it is filled with water. So this much amount of liquid in the column is going to exert some pressure. And how much will be that pressure? That is another unit. So it refers to an equivalent height of a column of liquid. For example, a pressure of 0.2 meter of water. The pressure will push the water column upwards about 0.2 meter. This can be converted into other units. So like, for example, if I say that Newton per meter square, it can be converted into Pascal. It's actually equal to Pascal. So we have different units: kilopascal, kilonewton per meter square, megapascal. You can convert Newton per meter square into megapascal. So similarly, the liquid column height is also a unit, and it is convertible. So you can convert the liquid column height for any fluid into Pascal or Newton per meter square. So for example, the conversion rate shown here is one of the conversion rates shown here is this, that 101.3 kilopascal. 101.3 kilopascal is the atmospheric pressure. It is equal to 10.33 meter of water height. So if I have a column of water which is filled with water, and the height of the water column is 10.33 meter, it's a very big height. You know, the height of the door would be like 2 meters. So you have 5 doors, one over the other. So if the column height is 10.33 meter, so the pressure exerted by this column of water would be equal to 101.3 kilopascal. The unit conversion. Okay. So the thing is that if it is a unit, then the unit conversion is also there. And we can actually determine the unit. But this is one of the kind of a unit conversion for which you do not need to memorize it. You will actually find it. You will actually calculate it yourself. Okay. Yeah, 0.2 kilo. But the thing is that this is the conversion rate. 10.33 is the conversion rate. Conversion rate, so 101.3 kilopascal equals to 10.33 meter of water column. Now, this is one very good question. Actually, this is a law that we are going to study today. There is a law which we are going to study, and the law says that the pressure is independent of the column cross section. Okay, pressure. We are talking about the pressure. It's independent of the column cross section. Okay, so the pressure would be the same. Yeah, obviously, if you're going to increase the column cross section or decrease the column cross section, the force applied will be different. Force might change based on the area, but the pressure would remain the same. So pressure, it's independent whether you have a small column, whether you have a very small cross-sectional area column, or you have a very big cross-sectional area column. Okay. So this is actually one of the laws that we are going to study today. Anyways, things are going to get much more clear to you as we proceed in this course. Okay, atmosphere. One atmosphere is the air pressure at sea level at standard conditions, which is approximately 15 degrees centigrade. The standard atmospheric pressure in various units. Okay, this is basically the conversion factors, but they are so common. I want you to memorize them. Most probably, some of these conversion factors might be provided in the exam if needed. But even if I do not provide it, this is something that we should memorize. Okay, so 1 atmosphere is equals to 101.3. Actually, it is 0.325 kilopascal, right? Or 101.325 Pascal. 101.325 kilopascal or 101.325 Pascal. Okay, which is equals to 1.01325 bar, because 1 bar is equals to 10 to the power 5 Pascal, which is equals to 14.7 psi, which is equals to 10.33 meter of water column. As I told you, meter of water column is also a unit. But this thing equals to 10.33 meter of water column, which is equals to 760 millimeter of mercury column. So if I have a column filled with mercury, so that the height of the mercury column should be 760 millimeter, then this much height of the mercury column will exert the same pressure as equal to the pressure of atmosphere. Okay, which is equals to 29.92 inch of mercury column. Mercury column could be also expressed in inches or millimeters or meter or centimeter. Okay, so these are some of the conversion factors between different pressure units for atmosphere. And it is better if you memorize it, because when you'll be solving problems and if you know the conversion factors, really it won't take much of your time. Okay, things will become comparatively smooth while solving the problems. 1 bar is equals to 10 to the power 5 Pascal. So far everything is clear? Okay. Now we have some very important concept here, which is the absolute gauge and vacuum pressure. Now, this is the same concept which we studied in the course of thermodynamics. And since most of the students are those who have taken this course from me, so I hope that you know it. But if you don't know it, it's okay. We are studying it here again. Okay. Absolute gauge and vacuum pressure. Okay, this concept is very fundamental here in this course. Okay, so I want you to pay a little focus on it. Okay, okay, let's first try to understand the concept of pressure. Now, suppose I have a container and there is air inside the container. Now, the container will have a certain pressure in it. The question is that why is there pressure inside the container? Why the container is experiencing some pressure? Now, if you go deep, so you realize that the air is composed of molecules. The molecules are in constant motion with each other. The molecules collide with each other. They also collide with the walls of the container. And when the molecules collide with the walls of the container, they exert a certain pressure over the container surface, okay? And so the container feels the pressure. This is the basic theory. This is the basic concept. Why does any container feel, or anything feels the pressure? The pressure is felt because something is pushing against it. So if the container is filled with air, the air molecules are in motion, they collide with each other, they collide with the walls of the container, and so the container walls feel the pressure. Is the concept clear? Okay. Now, if I want to remove, or if I want to reduce the pressure, what do I have to do? What I do is that one by one, I remove the molecule of air from the container. So less number of molecules means less pressure. So I keep on removing the air molecules from the container. What's the maximum I can do? The maximum I can do is that I can remove each and every molecule of air from the container. So now there is not even a single molecule of air inside the container. And that is a point when we have vacuum inside the container. I'm talking hypothetically. I'm not saying is it possible in this world, not possible. I'm just talking conceptually. So if I have removed each and every molecule of air from that container, now there is no molecule which can collide with the wall, and so the wall cannot experience any pressure. So there is vacuum inside. And so what will be the pressure inside? Zero. We call it vacuum. Absolute zero pressure. Now, can the pressure be negative? Now, with this definition, pressure cannot be negative. What maximum can we do? We can remove each and every molecule from the container, and that's it. Pressure can become zero with this concept, with this theory, cannot become negative. So this is the concept of pressure. We call it absolute pressure. And absolute is something, it's something in mathematics, a function. When you apply absolute function to anything, it can never become negative. It will always be either positive or minimum zero. That's why we have absolute temperature. Absolute temperature is the Kelvin temperature scale. Can it go negative? Can there be negative Kelvin? No, not possible. The minimum is 0 Kelvin. Right? So in the same way, based on the same concept, we'll have absolute pressure. So for the case of absolute pressure, our reference point is absolute vacuum, zero pressure. This is our reference point. From this reference point, we are judging any pressure, whether the pressure is high, low, whatever it is. But our reference point is vacuum. Right? So do you understand the concept of absolute pressure? Now let's discuss the concept of gauge pressure. Now, you see, we live in the atmosphere, so the atmosphere is all around us. When the atmosphere is all around us, the atmosphere has a pressure, and that pressure is being exerted over us all the time, but we are comfortable in it. We know that the pressure is being exerted on us, but we don't feel any discomfort, because this is the atmospheric pressure, and we are made to survive in atmosphere. So for us, if we consider atmospheric pressure as our reference point, so for this point, we will say that, okay, our gauge pressure, then we call it as a gauge pressure. So our gauge pressure, 0 is the atmospheric pressure. Because this is our reference point, it's okay. So when we say a pressure is higher, when we say a high pressure, so we refer to the atmospheric pressure. Higher than atmosphere is considered as a high pressure. Lower than atmosphere would be considered as lower pressure or vacuum pressure. We can call it vacuum pressure. Okay. So the difference between absolute and gauge pressure is our reference point. If our reference point is the vacuum, then the pressure that we are going to measure will be the absolute pressure. Vacuum is zero, but whatever the pressure we are measuring, if based on the reference of vacuum pressure we are measuring, we call it absolute pressure. But if based on the reference of atmospheric pressure, if our reference point is the atmospheric pressure, then we don't call it absolute pressure, we call it gauge pressure. Okay, so let me give you an example. Okay, look here. Here, let's say this is the point of P equals to 0, or I can say P absolute equals to 0, which is basically the vacuum. Okay, so this line is the vacuum line, absolute 0. Okay, now suppose if I'm saying that the atmospheric pressure is 101 kilopascal, so I will draw a line higher than this line, and this line would be at 101 kilopascal. So this will be my atmospheric pressure, P atmosphere. Okay, so I will say here P atmosphere is equals to 101 kilopascal absolute or 0 kilopascal gauge. P atmosphere is 101 kilopascal, but 101 kilopascal, when I'm saying 101, I'm taking the reference as the vacuum. So this is absolute value. But when I'm saying 0, so that means I'm taking the reference atmospheric pressure as the reference. So the reference point is considered as 0, right? So if I take atmospheric pressure as the reference, then atmospheric pressure is 0. Okay, so it says 0 gauge. So it is 0 gauge. Okay. Now suppose I say that I have, let's say I have a ball, and I say that the pressure in the ball is, say, 200 kilopascal. Okay, pressure inside the ball is 200 kilopascal gauge. If I'm saying this 200 kilopascal, it is gauge, that means actual absolute pressure from the vacuum would be atmospheric pressure plus 200 kilopascal. Okay, because whenever I'm saying gauge pressure, so gauge pressure is always relative to the atmospheric pressure. So atmospheric pressure is 101 kilopascal, and 200 kilopascal is higher than 101 kilopascal. So 200 kilopascal higher than 101 kilopascal will be 200 kilopascal gauge. Or in terms of absolute, if I'm taking from the absolute value, it will be 101 plus 200. Okay, combine them together, so that will be 300 kilopascal absolute. So at an atmospheric pressure of 101 kilopascal, 200 kilopascal gauge is equals to 301 kilopascal absolute. So let me repeat the sentence again. At an atmospheric pressure of 101 kilopascal, 200 kilopascal gauge is equals to 301 kilopascal absolute. You get the idea? Okay. So we get an equation here that P absolute should be equals to whatever the P atmosphere plus P gauge. You get this equation. P absolute is P atmosphere plus P gauge. Okay. So if I know the absolute and atmosphere, I can find gauge. If I know the atmosphere and gauge, I can find absolute. If I know the absolute and gauge, I can find atmosphere. First of all, what does gauge means? In English, gauge means an instrument to measure. Gauge, what does gauge mean? In English, gauge means an instrument to measure. So very first time when the vehicles were introduced, so they started using tire which was filled with air. They wanted to know that what is the pressure of air inside the tire. So you go to the market, you find a pressure gauge. The pressure gauge is a device to measure the pressure. When the pressure gauge is not connected with anything, it is giving zero reading. It is giving zero reading, but it does not mean there is zero pressure absolute outside. Okay, that does not mean that we are living in vacuum. It is giving zero gauge, means equal to atmospheric pressure. Now, if you connect that gauge to the tire, it's going to give you how much is the pressure of the tire higher than the atmosphere, relative to atmosphere. So the reading given by the gauge is basically the gauge pressure. The reading given by the pressure gauge is the gauge pressure. And gauge pressure is always relative to atmosphere. How much value higher than atmosphere? So for the gauge, reference is always atmospheric. Okay. So when I'm saying 200 kilopascal gauge, it means 200 kilopascal higher than atmosphere. When I'm saying 50 kilopascal gauge, it means 50 kilopascal higher than atmosphere. When relative to. When I'm saying 10 kilopascal gauge, it means 10 kilopascal higher than atmosphere. It's clear? Now, if I'm saying 200 kilopascal absolute, this does not mean now I'm referring with the atmosphere. Absolute always means we are referring from absolute vacuum. We are taking the reference as absolute vacuum. Okay. So 200 kilopascal absolute means 200 Pascal compared to absolute vacuum. Okay. Irrespective of whatever the atmospheric pressure is. So absolute means always referring to the vacuum. Absolute vacuum. But gauge means always refer to the atmospheric pressure. Is this point clear or not? Okay. In the same way, we have another instrument through which we can determine if the pressure of something is lower than atmosphere. Suppose if I have a ball, inside the ball, the pressure is lower than atmosphere, then the pressure gauge is not going to give me the reading, because pressure gauge is always going to give me the reading higher than atmosphere. So I need another instrument, and that instrument could give me the reading for the pressure lower than atmosphere, but it will give me again with reference to the atmosphere. So it's going to, so I'm going to the market and I'm going to purchase a vacuum gauge. We call it vacuum gauge. So pressure gauge, vacuum gauge. Pressure gauge, if the is an instrument to measure pressure higher than atmosphere. Vacuum gauge is an instrument to measure pressure lower than atmosphere. And what reading it will give? It will give the reading that how much lower than atmosphere the pressure is. So if the vacuum gauge reading is 30 kilopascal, it means 30 kilopascal below atmosphere. So if the atmosphere was 101, so 30 kilopascal vacuum means 101 minus 30 means 71 kilopascal absolute. Okay, so whenever I have the vacuum reading, so vacuum reading, again, vacuum reading like gauge is taking the reference point as the atmospheric pressure, but gauge value gives the reference point as atmospheric pressure, takes the reference point as atmospheric pressure and give how much higher than atmosphere. Vacuum gives the reading how much lower than atmosphere. Okay, so if I say that P vacuum is equals to 50 kilopascal, that means my value of pressure, actual value, absolute value of pressure is 50 kilopascal below atmosphere. If the atmosphere is 101, so 101 minus 50 equals to 51 kilopascal will be the absolute pressure. That will be the absolute pressure. Okay. So 20 kilopascal vacuum means 20 kilopascal lower than atmosphere, whatever the atmosphere is. 30 kilopascal vacuum means 30 kilopascal lower than atmosphere. 80 kilopascal vacuum means 80 kilopascal lower than atmosphere, whatever the atmosphere is. And you know that the atmospheric pressure vary with elevation. Here, right now in Karachi, the atmospheric pressure would be 101 kilopascal. But if you go to a high elevation in Murray, somewhere, the pressure lowers. Okay, so there are low pressure. At high altitude, the pressures are low. So the atmospheric pressure will vary from the location. Based on the location, based on its elevation, the atmospheric pressure will vary. Okay, so here the point is that you need to understand what are the differences between absolute gauge and vacuum pressures. So absolute pressure, okay, based on this, the equation for the case of vacuum pressure would be what? P absolute will be equals to P atmosphere minus P vacuum. P atmosphere minus P vacuum. Okay. So if the atmosphere was 101 and the vacuum pressure was 50 kilopascal, so absolute pressure would be 50 kilopascal below atmosphere, means 101 minus 50, so that is 51 kilopascal. So now we have two equations here. P absolute is equals to P atmosphere minus P vacuum, or P absolute is equals to P atmosphere plus P gauge. Is it clear? Okay. So just to summarize, if I am taking my reference point as the absolute vacuum, then whatever the pressure reading I'm getting is the absolute pressure reading. And absolute pressure reading is the actual pressure. Okay. But if I'm taking my reference point as the atmospheric pressure, then gauge pressure is how much the pressure higher than atmosphere, and vacuum pressure is how much the pressure lower than atmosphere. Is it clear? Okay. So this is why P vacuum is also given another name. P vacuum is equals to negative P gauge. Because gauge pressure is always higher than atmosphere. So if I take the negative gauge, that will be the P vacuum. Because P vacuum is lower than atmosphere. Okay. That's why P vacuum is also given a name as negative P gauge. Okay. So P absolute is whenever the pressure is measured from the absolute vacuum. P gauge is whenever the pressure is measured with reference to the atmospheric pressure, and it is normally considered higher than atmosphere. Okay. And if the value of the pressure measured is with reference to the atmospheric pressure, and it is mentioning how much lower than atmospheric pressure, then it is P vacuum. Okay. And if you know P vacuum and P atmosphere, you can find what is P absolute. And if you know P gauge and P atmosphere, you can find P absolute. In case of vacuum pressure, absolute pressure will always be lower than atmosphere. In case of vacuum pressure, the absolute pressure will always be lower than atmosphere. Okay, so if the atmospheric pressure is 101 kilopascal and the vacuum pressure is 10 kilopascal, so what will be the absolute pressure? So 10 kilopascal lower than 101, so that will be 91 kilopascal. Okay. Okay, so let me give you a small exercise to do it here right now. Let's say that the P gauge is 34 kilopascal and P atmosphere is 91 kilopascal. Find out what will be P absolute. P gauge is 34 kilopascal, P atmosphere is 91 kilopascal. Find out what will be the absolute. Yeah. Yeah. Okay. Now suppose if I'm saying that the instead of P gauge, I'm saying this is P vacuum. If P vacuum is 34 kilopascal, P atmosphere is 91 kilopascal, what will be P absolute? So it will be 91 minus 34, right? So I don't know how much. Okay. Is this thing clear? Okay, tell me one thing, that if P absolute is 100 kilopascal and P vacuum is 30 kilopascal, then tell me what will be P atmosphere? Yeah, 130. P absolute is 100, but vacuum is 30. So P atmosphere should be 130. So for 130 P atmosphere, if I go 30 kilopascal down, then it will give me the P absolute 100. Okay, if I say that P absolute is 100 and instead of P vacuum here, I'll say P gauge. Here is 30. Then what will be P atmosphere? 70. So I think the concept is not clear to everybody. This concept is very important, whether we are talking about absolute pressure or we're talking about gauge pressure. For the gauge pressure, atmospheric is always 0. So atmospheric pressure is equals to 0 gauge pressure. Is there anything which is not clear so far? Okay, pressure transmission. In a closed system, a pressure change produced at one point in a system will be transmitted throughout the entire system and to the walls of the container. This principle is known as Pascal's law. You studied Pascal's law before, right? I think you started studying this law from secondary education somewhere. So it's a very common fundamental law, and this law basically is talking about the pressure transmission. So suppose I have a fluid body here, which is a continuum body. This is a continuous fluid body. I have a fluid body here. So if I change the pressure at one point, automatically that pressure change is transmitted throughout the entire fluid body. If I change the pressure at any one point, that change of pressure is transmitted throughout the entire body. So the entire body faces it. Okay. So this is known as the Pascal's law. So in a closed system, a pressure change produced at one point in a system will be transmitted throughout the entire system and to the walls of the container. This principle is known as Pascal's law. So this is a small definition which I want you to memorize. Okay. Hydraulic machines. Hydraulic machines use fluid to transmit force or energy to assist in the performance of human tasks. Examples include hydraulic car, jack, braking system, forklift trucks, power steering. The power steering is something I've, I have faced it a lot. Initially, I used to have a car which was manual. A lot of power is required to turn the steering. But once you have the power steering, hydraulic fluid does all the work. Even you can turn it with your finger. Okay. The thing is that using hydraulic machines, we have the mechanical advantage. Mechanical advantage means now I do not need to do all the work. I will do some of the work, and then a lot of work would be done by the machine itself. Okay. So hydraulic machines provide mechanical advantage, which is defined as the ratio of output force to the input force. So our input force required becomes significantly less, okay, because of that. And this is all working because of the Pascal's law. You apply the pressure, you apply the force at one point in the fluid system, and that force which you have applied, the pressure is transmitted throughout the entire fluid. Okay. And this is the Pascal's law, because of which the hydraulic machines are possible, and they provide the mechanical advantage. Okay. So we have a numerical here, which is going to give us some insight into it. So let's go through with this numerical. A hydraulic jack has the dimensions shown. You know what is a hydraulic jack? Normally, if you want to lift the car, okay, or sometimes you have to change the tire, so we use the hydraulic jacks. Okay. So hydraulic jack has the dimensions shown. If one exerted a force of 100 Newton, so a force of 100 Newton applied on the handle of the jack, what load F2 can the jack support? Okay. So first, have a look at the jack. How does the jack look like? Okay, so you see you have a lever in the jack. This is the lever. Okay, this lever is connected to a small piston. Now this piston is in connection with a small container of water or whatever the oil, hydraulic oil we have. Okay, so we have a hydraulic oil here. This oil is connected with another piston which has a large area. Okay, so this is another piston which has a large area, and at the top of the piston we have the load. So if I apply the force here, automatically when this lever goes down, this piston goes down, this piston goes down, and automatically this piston will move up. Okay, so this is the hydraulic jack. Okay, so you apply the force over the lever, this piston goes down, and this one goes up, and it lifts the load. Okay, so now we're going to see that how this Pascal's law helps in actually the operation of the hydraulic jack. So here, for the case of this hydraulic jack, the lever is 30 centimeter. Okay, and between the fulcrum point and the this is the load, right? Between the fulcrum point and the load, this is the effort. You know, in case of the lever, we have a fulcrum, we have a load and effort. Okay, so effort will be applied here. Okay, the load will be here, and this will be the fulcrum point. Okay, so here in this case, 30 centimeter is between the effort and the load, and between the load and the fulcrum, it is 3 centimeter. Here we have this piston. The piston is circular in diameter, and it is 1.5 centimeter diameter piston. Then we have another piston, the larger diameter piston. This is actually 5 centimeter diameter piston. Okay, we call it this as a lifter. This is the lifter, because this is going to lift the load. Okay, we have a check valve here. I don't need to discuss the importance of this check valve here. And obviously the load will be lifted here. So here we'll have the load lifted. Okay, so this is basically the dimensions of the hydraulic jack. So now let's see the solution of the problem. First of all, do you understand the problem statement first? Okay, we just want to know that if 100 Newton force is applied at the effort, how much load can be lifted by the lifter? By applying 100 Newton, how much load can I lift? So this is the question. Okay, and do you understand the mechanical construction of this hydraulic jack? So now let's try to solve the problem. Okay, let's move towards the solution of the problem. Okay, the first thing that I need to find is if I apply 100 Newton force here, I need to know how much of the force is transmitted by this small piston. Okay, how much force will be transmitted by this small piston? Okay, if I apply 100 Newton force here. So what I can do is that I can do I can solve the equilibrium of moments at the fulcrum. Fulcrum is the main point of contact where the rotation occurs. Okay, so I can apply the moment equilibrium at the fulcrum. So I can find out that what would be the force provided by the piston because of my application of 100 Newton. Okay, so what I have to do is that I have to take the summation of moment at point C. Okay, so because of this 100 Newton, so the moment will be 100 Newton multiplied by the moment arm. So what will be the moment arm here? It will be 33. 30 plus 3. Okay, and then I'll have the piston here, and the piston here, the force applied by the piston. So this force multiplied by the moment arm here. Okay. So let's have a look here. So 33 into 100 minus 0.03 into F1. F1 is the force, or you can say the reaction force over the piston. Okay. So the force comes out to be 1100 Newton. First of all, till this step, is it clear or not? Okay. Why there is a negative sign here? One moment is in a clockwise direction, the other moment is in anti-clockwise direction. If I'm taking the equilibrium at the fulcrum. Okay, so you can see here. Here the moment is in the anti-clockwise direction, and here the moment is the clockwise direction. So obviously they two will be negative. Okay, so but with this I can determine that how much is the force applied by the piston. Okay, so by applying 100 Newton of force, 1100 Newton of force is applied by the piston. Okay, now if I know that how much is the force applied by the piston, I can determine what is the pressure applied by the piston. Okay, so what's the formula? The formula is pressure. I will say here P1 is equals to force F1 over area A1, right? So here this will be my force F1. This will be my force F1. Similarly, the area of this piston will be A1. So I can determine how much is the pressure applied at this point. Okay. Now finding out, okay, one thing is clear that I have already determined how much is this force, and it is here. This is this force, right? Can I find out the area? Because I know the diameter. And if I know the diameter, then I can find out the area. So what's the formula for the area? If I know the diameter, pi r square or pi d square by 4. Okay. So if I know the diameter, I know. So I know this F1, I know A1, so I can find what is P1. Is it clear? So this is the pressure applied by the piston on the hydraulic jack, by the piston 1. Now here comes the Pascal law. The Pascal laws say that if you apply a certain pressure, at any point in the on the liquid, on the fluid, that pressure is being transmitted throughout the entire fluid. So whatever the pressure applied at this point 1 will be the same pressure that will be applied here at point 2. Where, because this is the fluid which is in contact with piston 1 and piston 2. So if the piston 1 is applying certain pressure, the same pressure will be transmitted to piston 2. Okay. So the pressure here, pressure at this point, P2 will be the same as P1. This is Pascal's law. Because the fluid is a continuous body here. You apply pressure anywhere and it will be transmitted throughout the entire fluid. This piston P1 has applied pressure at this point, not here. But because of Pascal's law, the pressure which is applied here is directly transmitted there as well. Okay, so the same pressure is going to be applied at piston P2. Okay, so now we know what is the pressure P2 which is applied because of the Pascal's law. So come back here. So I know P1 here. If I know P1, that means I know what is P2. And this P2 should be equals to F2 divided by A2. And I wanted to know what is F2. How much is the load that the lifter can lift? So if I know, now I know P2, if I know A2, I can find F2. Now what is A2? Again, because it is a circular body. Okay, so pi r square or pi by 4d square. And we know the diameter of the other piston as well. So I can find A2. So I will find what is F2. What's the value of P1? You can see here. It's you see here 1100. 1100 was the force divided by pi d square by 4, and the diameter was I think it was how much 1.5 centimeter. So you can convert it into meter. Okay, so this will be the diameter. So pi d square by 4. If you just substitute the values, you're going to get 6.22 times power 6 Newton per meter square. Is it clear? Okay. So if you have P1, then we'll say that P1 is the same as P2. Okay. This is by Pascal's law. So if there was no Pascal law, P1 would never be equal to P2. It's coming different. हो सकता है इधर कैलकुलेशन में कोई मिस्टेक हो 1.5 सेंटीमीटर डायमीटर है so 1.5 centimeter diameter का मतलब हो गया if I let's say if I put it in 0.75 centimeter, so divided by 100 square into pi. See? So is it coming the same value written on in the question? Your calculation was wrong. Normally a mistake honi nahi chahiye because this is book. So once they make the book, they do it proofreading 1 time, 2 times, 3 times to eliminate all the mistakes as possible, as much as possible. But anyways, this is okay. This is understandable. Okay, so the amount, so the actual value of force which can be lifted is 12.2 kilonewton. Means 12,200 Newton. So actual amount of input force was 100 Newton. Like 122 times is the mechanical advantage. The force which we are applying on the lever, 122 times more force is being, more load is being lifted by this, by the lifter of this jack. And this is understandable. If you look at a car, it's so heavy, if I want to lift it, I can never lift it. But with the help of a hydraulic jack, I can lift the car easily. Is the solution clear? Now this is for the case here actually if both the elevation are same here, then we can find out the ratio like this for the mechanical advantage. But if the elevation is different, then our ratio would be slightly different. We are going to study it, but not right now. Okay. So just keep this to review later. So if the elevations are different between the first piston and the second piston, point of contact with the liquid, if the 2 point of contacts are at different elevation, then the formula would be a little different. Okay. And the reason for that difference we are going to discuss later. We're going to study it. Pascal's law is done here. Do you understand the Pascal's law? Do you understand its application? Okay, so now let's move towards another topic, which is pressure variation with elevation. Okay. So we are going to develop the hydrostatic equation for the pressure variation with elevation. You're going to listen the word this a lot, hydrostatic. You need to understand what is it. Hydro means liquid. Hydro means, in reality, you're right. Hydro actually comes from water. The Greek for water was hydro. Okay, so hydro means in reality water, but here we, in general sense, we always say means liquid. When we just say fluid, it means liquid and gas both. But if I have to focus over liquid only, then I call hydro. Okay. So hydrostatic. Static means the liquid which is not in motion. Static, at rest. Okay. So hydrostatic, liquid at rest. Okay. So let's say that I have a static fluid. Let's say I have a static fluid, and the basic hydrostatic differential equation states that for a static fluid, the pressure varies only with elevation within the fluid. Okay. So suppose I have a cylindrical fluid element. This is a cylindrical fluid element. So it's a cylinder made up of fluid. Okay, the length of this cylinder is del L. The cross-sectional area is del A. Is the cross-sectional area. Okay, so this cylindrical element is making an angle alpha from the horizontal. Okay, now what I can do is that I can apply the force balance, equilibrium of forces. If I apply the equilibrium of forces, so there will be force due to the pressure on the fluid at this end. There will be force due to the pressure on the fluid at this end. Okay, and there will be the weight of the fluid element. Weight of the fluid element will be acting downward. Okay, so we have the force of pressure minus force of weight equals to 0. This will be the equation. Okay, now force of pressure will be what? P del A. If this pressure is in this direction, the other pressure will be in the opposite direction. Okay, plus P plus del P into del A. Okay, minus force of the weight. Force of the weight is basically what? Mg. Okay, so Mg, or mass can be written as density into volume. Okay, so I will write here volume into density into G. Right, and density into G is gamma. So I can write here volume into gamma. And the volume will be what? Volume will be cross-sectional area multiplied by the length. Okay, so del A into del L into gamma. Right? So this is the force of the weight, but not the whole force of the weight will be acting in this direction. We want to find out the force of the weight acting in the direction of the pressures. Okay, so if it is making an angle alpha here with the horizontal, okay, so it will be sine alpha, will be the component of the weight acting in the cylindrical axial direction, okay, along the axis of the cylinder. So multiply by sine alpha. Okay, so this P delta A will be cancelled by this P delta A here. So we're going to have delta P delta A minus gamma del A del L sine alpha equals to 0. We can divide the whole equation by del L del A. So we'll get del P by del L equals to negative gamma sine alpha. Okay. Now sine alpha can be written as del Z by del L. Okay. If you look here, it becomes this right angle triangle. Yeah. So if I just substitute the value of sine alpha here, so the general equation which I get is this: dP by dZ is equals to negative gamma. This is the basic hydrostatic differential equation. So if I have a fluid which is not in motion, it is static. So the pressure in the fluid will vary with elevation only. Pressure in the fluid will vary with elevation only. Okay. And how much is this variation? This variation is equals to negative gamma, where gamma is basically rho g, density into gravity, associated due to gravity. Exactly. Both can means it happens in gas as well as in liquids. The only thing is that in case of the gas, density is very small. So the actual value of variation will be negligible. Density of water is 1000 kg per meter cube. Density of air is 1. How much is the difference? About 1000 times. So the variation is there, but that variation for our practical purposes is almost negligible. So for the case of gases, we ignore. But for the case of liquids, it's not ignorable. So you have a variation in the elevation and significantly change in the pressure would be observed for the case of liquid. For the case of gases, yeah, if you go from here to Murray, yeah, then you might see the difference. But on a smaller scale, you won't feel the difference. If I'm standing at the top of this building and if I'm standing at the ground floor, the difference would be negligible. Okay. So, but if I'm standing in Murray, somewhere at the high elevation, or in Himalayas, or if I'm standing in Karachi, I can feel the difference. On a very large scale, the difference is visible for the case of gases. But on small scale, we ignore the difference. Okay. So the thing is that this equation is very significant here. And this equation gives us some valuable information. First of all, pressure varies with elevation only. So if I have a container of fluid, the pressure at the same elevation will be same. So the pressure here would be the same as pressure here, would be the same as pressure here, would be the same as pressure here. It only varies if the elevation changes. So the pressure here will be different than the pressure here. So first thing is this: the pressure variation in static fluid is only with elevation. So dP by dZ. And this variation is a constant variation, is a linear variation. And it has a specific value equals to gamma, rho g. Okay. And there is a specific significance of the negative sign here. Significance of negative sign is what? It shows that if your elevation increases, the pressure will decrease. So if I have a container filled with liquid, the higher I go in the liquid, the lower will be the pressure. The lower I go in the liquid, higher will be the pressure. If ever you have an experience to go into the swimming pool, try to deep dive. you will feel the pressure. The more depth you go inside, you will feel more pressure. So this thing is quite visible. You can experience it on your own. Okay? So at higher elevations, comparatively, the pressures are lower. So you increase the elevation, the pressure decreases. You decrease the elevation, the pressure increases. Okay. So this thing is visible by the negative sign here. The negative sign signifies that the relationship between the pressure and elevation are inverse. If you increase the elevation from the ground, that the pressure will reduce. And if you decrease the elevation, if your elevation is going down, then pressure will become high as you move down. Is it clear? So change of pressure occurs only when there is a change of elevation. Therefore, pressure is constant everywhere in a horizontal plane. On a horizontal plane, the pressure is constant. If the elevation Z is taken positive from the ground up, then the pressure changes inversely with elevation. So these are 2 points which are very important from this hydrostatic equation of pressure variation. This is the hydrostatic equation of pressure variation. Is this thing clear so far? So we have dP by dz is equals to negative gamma. Or I can write here dP equals to negative gamma by dz, negative gamma multiplied by dz. Or I can write here dP plus gamma dz equals to 0. Right? If gamma is independent of elevation, if gamma is basically what, rho g, is a fixed quantity, and if the density is also not varying, it's also constant, then I can put this gamma inside the differential. Okay, so we can write here dP plus d gamma z equals to 0, or I can take this common, so differential of P plus gamma z equals to 0. So differential of P plus gamma z equals to 0. If I do the integration here, if I integrate it, then d will be finished. Integration is the opposite of differential, right? So it will become P plus gamma z equals to not 0, constant. When you integrate it, and if you do, see, when you integrate it and you don't have the limits of integration, then you get a constant, right? So this thing is constant. So this thing is written. P plus gamma z is equals to constant, right? Now P plus gamma z together, P plus gamma z together is known as piezometric pressure. Now there are different pressures here. You have to start understanding them. P is hydrostatic pressure. P plus gamma z is Pz, which is piezometric pressure. P is hydrostatic pressure. P plus gamma z is Pz, which is piezometric pressure. So what's the difference between hydrostatic pressure and piezometric pressure? In case of piezometric pressure, you also take into account gamma z, and gamma z is basically what? Gamma z is the pressure due to elevation. Kinetic energy, potential energy. Potential energy. What's the formula of it? mgh, right? So this is basically the potential energy due to elevation. So we have a hydrostatic pressure, means the pressure of a fluid in itself. Then if that fluid is at a certain elevation, so there will be potential because of its height as well. Include the two together, whatever the pressure, we call it piezometric pressure. Okay. So this is in terms of pressure, all in Newton per meter square or Pascal. This is in Pascal. Gamma Z is also unit has Pascal. If you put the unit of gamma, put the unit of elevation, okay, the combined will be Pascal. You can check it yourself if you want. Okay. Now, what we, as I told you, that we have also a pressure column height as a unit. So what we can do is that we can divide this equation by gamma. So it will become P by gamma plus Z equals to constant. If you divide this equation by gamma, then it will become P by gamma plus Z is equals to constant. And we call, now this is the unit of height. Z has the unit meters. P upon gamma will also have unit meters. You can check it if you want. You know the unit of gamma, you know the unit of pressure, put it. In the end, you will get a unit of meter. Okay. So now this is known as piezometric head. Head always refers to the length, column height. So we call it column head. Okay. So this is known as piezometric head. Okay. So piezometric head is a combination of elevation head plus hydrostatic head. Hydrostatic pressure is P. Hydrostatic head is P by gamma. Elevation, pressure due to elevation is gamma Z. Elevation head is just Z. Piezometric pressure is PZ. Piezometric pressure head is H. Here H means P upon gamma plus Z. Things are getting a bit confusing. Height. No, gamma is not angle. Gamma, actually, you missed the first class, I think. So gamma is basically a specific weight. Specific weight, gamma is equals to rho G. Okay, when we were discussing in the very first lecture, the fluid properties. So we discussed three things: density, specific weight, specific gravity. Specific weight is gamma. Okay. So, but the videos are already recorded and you have the videos. When you go through it, you're going to understand. Okay. So we have hydrostatic pressure, we have pressure due to elevation. Combine them together, we have the piezometric pressure. These are all in the pressure units. Everything will be in Pascal, Pascal, Pascal. Then we can also have the same equation in the head units. Okay. And if we have in the head units, then we have the hydrostatic head, P by gamma, plus elevation head, which is Z, whatever the elevation, equals to piezometric head. We call here H, and this H is basically combination of these two things. So these all have units of meter. Now the thing is that P plus gamma, P over gamma plus H is a constant. Means if I have a container at any point, this combination would be the same. Now try to understand, you studied this in physics as the conservation of energy. The sum of kinetic and potential energy is same whether something is sitting on the ground or it is there at the top. Right? You studied it. Okay. So when something is falling from the height, its velocity is increasing, so the kinetic energy is increasing. And why? Because the potential energy is being converted into kinetic energy. Right? You studied it. Right? So the total energy content is the same. So here we are saying in the same way, the total head is the same in the fluid. Okay. So at any point, let's say this is 0.1 in the fluid, this is 0.2, this is 0.3. At any point, 0.1, 2, or 3, the piezometric head would be same. So H1 will be equal to H2 will be equal to H3. Okay, and that means at any of these points, so P1 upon gamma plus Z1 will be equal to P2 upon gamma plus Z2 will be equal to P3 upon gamma plus Z3. If I have an fourth point, so P4 upon gamma over Z4. Okay. Now height might not be same. Height might be different, but if the height is changing, so the P value will also change. The combination will be the same. The summation will be the same. I'm not saying the height is same. At different heights, the hydrostatic pressure will also be different. But their summation would be the same. Is it clear? So P1 upon gamma plus Z will be equal to P2 upon gamma plus Z. The only thing is that it should be a continuous fluid. And it should be static. We're talking about the static fluid. We're not talking right now about the fluid in motion. We're talking about the static fluid. So for the case of the static fluid, the piezometric head inside the entire fluid would be the same. Whether you take the fluid material from the top, or you take from somewhere in the middle, or you take somewhere from the bottom. Piezometric head would be the same. Piezometric pressure would be the same. And piezometric pressure is a combination of hydrostatic plus pressure due to elevation. Okay. So if the elevation is changing, the other thing will also change to make the combination summation equal. Okay. So I can say that P2 minus P1 equals to negative gamma Z2 minus Z1. It's just by using this equation. So far things are clear. So far it's easy. It's going to get more and more deep. Okay. But hopefully you won't have much trouble if you follow through regularly. If you miss things, and anyways, you have the video lectures. Not a big issue. But. Okay, so piezometric pressure is equals to gamma h. Piezometric height multiplied by gamma. Piezometric pressure is equals to gamma h. Okay. Now you can consider this example. Suppose if I have this container, and in this container you have oil and water. So below you have the water, above you have the oil. I told you piezometric height is same. Piezometric head is same, but it should be the same fluid. If the fluid is changing, then it won't be the same. Because if the fluid is changing, density will change. Density change means gamma change. Okay. So, but if the density is same, if the fluid is same, the gamma value will be same. So the piezometric head will be same. So here, if you see here, point A, B, C, these 3 points are in water. So the piezometric head A will be the same as B, will be the same as C. Similarly, for the case of oil, E, F, D, E, F, all 3 points are in the oil. So piezometric pressure at D will be the same as piezometric pressure at E, will be the same as piezometric pressure at F. But piezometric pressure at E and piezometric pressure at C will not be the same, because the fluid is changed. E is in oil, C is in water. Is it clear? So you see here, HA, HB, HC are same. HD, HE, HF are same. But HC is not the same as HD, because the fluid is changed. You want a break? Yes. Okay. Let's have a break of 10 minutes and then we'll continue. Okay, let's see this numerical water pressure in a tank. What is the water pressure at a depth of 35 feet in the tank shown? Okay, so we have this tank. Okay, so this is a water tank. The bottom elevation of the tank is at 200 feet from the ground. The top elevation of the tank is 250 feet from the ground. The top elevation is considered as 0.1, and below the top elevation means the open surface of the water, 35 feet below, at 0.2. 0.2 is a 35 feet below. We want to know that what is the pressure of the water at this point. So this is what is needed. What is the water pressure at a depth of 35 feet in the tank shown? Okay, 35 feet from the open surface. So at this point, we need to find what is P2. This is what we need to find. This water is at 50 degrees Fahrenheit. First of all, do you understand the problem statement? What is asked in the question? Okay. So since we have studied that the piezometric pressure remains the same, piezometric pressure remains the same. So we are going to use the equation for the piezometric pressure or piezometric head, and it is this equation. P1 upon gamma plus Z1 equals to P2 upon gamma plus Z2. Okay, between 0.1 and 2. Because it's the same fluid, 1 and 2 are the 2 points in the same fluid. Now, if you look here, Z1 is something we know. We know what is the elevation of state of 0.1. Z2 is something we also know. What is the elevation of 0.2? Okay, we don't know the elevation of 0.2 directly, but we know that this is 200 feet. This we know the elevation here is 250 feet, and we know this is 35 feet. 35 feet below 250. So that will be 215, right? So 200 feet. So we know Z2. Okay, then P2 is something that we need to find. We need to find what is the pressure P2. P1, we know P1. Why? Because P1 is open to atmosphere. And whenever any fluid is open to atmosphere, so the atmosphere, it will have the atmospheric pressure, and the atmospheric pressure is considered as for the gauge readings, atmospheric pressure is considered as 0. So P1 will be 0 gauge. P1 will be 0 gauge. So P1 here it is written. If you see, P1 is atmosphere, which is equals to 0 gauge. So we know what is P1. Reference यहाँ पे किसको रखा है? We are solving the problem in gauge. Okay, we are solving the problem in gauge. अगर हमें if we had the value of atmospheric pressure with us given in the question, then we could use the value of atmospheric pressure at P1. If we wanted to solve the whole equation in absolute. Right now we are solving the whole equation in gauge. Okay. So we know what is P1. We want to find what is P2. We know what is Z1. We know what is Z2. Gamma is basically a property of the liquid, which is provided to you in the exam. So gamma for water is given here. In this case, the gamma for water is 62.4 pound force per foot cube. So in this equation, everything is known except for P2. We can just simply substitute the values and we can find what is P2. Is the solution clear? Achha. If I want to solve this problem, instead of using this approach, I would use a direct approach. And this direct approach would be very useful for you in future. So just have a look at it. In direct approach, what I will do is that I will always start from the point where the pressure is known. So I have 2 points here, 1 and 2. 2, I need to find out the pressure at 2, but I know the pressure at 1. It's 0. So I know the pressure at 1. So I will always start from the point where I know the pressure. So that will be point P1. Then if I'm moving above that point, then it will be plus. If I'm moving below, sorry, if I'm moving above the point, then it will be minus. If I'm moving below that point, it will be plus, because pressure increases as we go down, pressure decreases as we go up, right? So from 1, I'm moving down to 2. Since I'm moving from 1 down to 2, so I will put here plus. Pressure increase as we move down. plus gamma into H. I'm using a direct approach. Gamma into H. Gamma will be the gamma for water, which is given. Okay. And H will be how much height I have gone down from 1 to 2. So this is 35 feet. No, this is 35 feet. How much I'm going down from point 1 to 2? I'm using direct approach. So P1 plus gamma H is equals to P2. We wanted to find P2. Okay. So if I put the value of gamma here, H will be 35 feet and P1 will be 0. 0. So I'm going to get the value of P2, which will be the same as here. So either you can use directly this equation, this is also okay, or suppose if you want to apply this equation and then come up with this answer, this is also okay. This you can consider as a direct approach. H 35. From the first point, we have started from the point for which we know the pressure. From that point to the second point, how much is the distance? That will be the H. Okay. I'm in the vertical distance, because the pressure varies only in the vertical direction. Is this in clear? Actually, if you have the calculator, why don't you put the values and see? Gamma 62.4 multiplied by H 35. Can you multiply 62? 2184. It's approximate 2180. Okay. So this question is done. PSFG. PSF is pound per square feet. G is gauge. If it was absolute, if we were solving it in absolute, then it would be PSFA. PSIG, pound per square inch. PSFG, pound per square foot gauge. क्या आंसर आ रहा है आपका? It will be what? It will be 62.4 multiplied by 35. It's okay. इधर भी शायद यही आएगा, क्योंकि अगर आप इधर भी देखें तो बेसिकली बनेगा क्या? 250 minus 215, 35 ही आएगा ना इधर. 35 multiplied by 62.4. See? This is in PSIG. When you convert PS, pound per square foot, to pound per square inch. So divided by 144 होगा मेरे ख्याल से. Square inch and square foot नहीं है. Okay, now let's see this one. Oil with a specific gravity of 0.8 forms a layer 0.9 meter deep in an open tank that is otherwise filled with water. The total depth of the water and oil is 3 meters. What is the gauge pressure at the bottom of the tank? So this is the thing we have. We have this container. This container is filled with water, but what happened is that at the top of the water now we have oil. Okay, overall the height of the fluid in the container is 3 meters. Out of this 3 meters, 0.9 meters is the oil, the remaining is water. 2.1 meters is water. Okay, now what we need to find out, we need to find out that what do we need to find? We need to find out what is the gauge pressure at the bottom of the tank. Okay, so at the top of the tank, I can say this 0.1. At the bottom of the tank, I will say 0.3. And in between, where I have the oil-water interface, I will call it at 0.2. Okay. Now, as I told you, whether what you can do, there are two different fluids. So the piezometric pressure would not be the same, but at the interface, it would be the same. At the interface. Okay. So what I'm going to do is 0.2 per same over. Okay, at the interface. Okay, so what I'm going to do is that I can make an equation for the piezometric pressure between 1 and 2. Then I will make an equation for piezometric pressure between 2 and 3. And I can solve it. Okay, so for the case of 1 and 2, I will use gamma of oil. For the case of 2 and 3, I will use gamma of water. So first I use gamma for oil between 1 and 2. Now 1 is open to atmosphere. So we know that P1 will be 0. Okay. Z1 would be 3 because let's say I'm starting from the bottom. So at the top, it will be 3 meters. Okay. So that one will be 3. P2 I need to find out. Gamma of oil I will use. Okay, what was given? Given was the specific gravity of oil is 0.8. Now specific gravity is what? S is equals to rho of oil divided by rho of water. Okay, so S is known, rho of water is known. So we can find what is the density of oil. Okay, so gamma oil will be equals to rho of oil multiplied by G. Okay, so 0.8 multiplied by gamma of water, which is 9810. Okay, so this plus at 0.2, what is the elevation? It is 2.1. So I'll find what is P2. Then this is the P2 for the case of oil, and at the interface, this will be the same P2 for water. So I know what is the P2 for water. It will be the same. And then I will make the hydrostatic equation between 0.2 and 0.3. So P2 upon gamma of water plus Z2 equals to P3 upon gamma of water plus Z3. Okay, so now I know what is P2. I know what is gamma of water. I know what is Z2. I know what is Z3. I can find what is P3. Now I can do it in the form of a direct approach. If I do it directly, always start from a known pressure. So what is the known pressure here? It is 1, right? So P1. Then I'm first moving from 1 to 2, right? So I'm moving down. Since I'm moving down, so it will be plus gamma H, but gamma will be for oil, and here the height will be of oil. Okay. Now I have come to 0.2. Now I'm further moving from 2 to 3. So again I'm moving down. So plus gamma of water plus height of water from 2 to 3 equals to, now I have come to 0.3 equals to P3. Direct approach. Now please solve it. So P1 is 0. Okay. Gamma of oil is 0.8 multiplied by 9810. Height of oil is 0.9. Gamma of water is 9810. Height of water is 2.1. So please find out what is P3. I have done it in one step. Direct approach. So please do it and cross check if you are getting the same answer. You should be getting 27.7 kilopascal gauge. Yeah, it's okay. 27.7 kilopascal gauge. Is it okay? It's the same problem. Water occupies the bottom 1 meter of a cylindrical tank. On the top of the water is 0.5 meter of kerosene, which is open to the atmosphere. If the atmosphere is 20 degree, what is the gauge pressure at the bottom of the tank? That's the same problem. Now, pressure variation for compressible fluid. Now, compressible fluid means air or any gases. Liquids are considered incompressible. Okay. So if the compressible fluid is air or sometimes some fluid which follows the ideal gas equation of a state, okay, then we know that dP by dz equals to negative gamma. If you know dP by dz equals to negative gamma, but gamma is rho g. But for ideal gas equation of a state, P is equals to rho RT. So rho is equals to P upon RT. Okay, so if I just substitute the value of gamma here, sorry, value of rho here, so it will become PG upon RT. Okay, so it becomes dP by dz equals to negative PG upon RT. So the hydrostatic equation for pressure variation becomes this for the case of compressible fluids, okay, where ideal gas equation of law is valid. Let's talk about our atmosphere. Our atmosphere is composed of air, which is compressible. Okay, so initially at the bottom level, we have troposphere, and then above troposphere, we have a stratosphere. Okay, now troposphere is till 13.7 kilometer. From the sea level till 13.7 kilometer, we have troposphere, and it follows a specific trend that there is about 5.87 Kelvin drop of temperature per kilometer. So every kilometer you move up, there is about 5.87 Kelvin drop of temperature. This continues in the troposphere until you reach 13.7 kilometer, and then the troposphere finishes and we enters into stratosphere. Now within the stratosphere, there is a specific range from 13.7 kilometer to 16.8 kilometer where there is no change in temperature. So temperature remains fixed. Okay. And after that, there is a slight increase in temperature. Okay. So suppose if we are dealing with the troposphere. So for the case of troposphere, we can actually determine the pressure variation by substituting the temperature gradient that we have within troposphere into the into the equation for pressure variation. So we know the temperature variation, place it into the equation for pressure variation. We are going to get the equation for the pressure variation, which is this. So P equals to P naught T naught minus alpha Z minus Z naught divided by T naught power G divided by alpha R. Okay. Now here we T naught, P naught, and rho naught are basically what? These are the reference points, level conditions, sea level conditions. Okay, so consider T naught as 15 degree, P naught as 101.325 kilopascal, rho naught is 1.225 kg per meter cube. When we are in the stratosphere, the temperature is constant. It's uniform temperature in the earlier zone. Okay, so if we put temperature constant, then our equation for the pressure variation becomes like this. So it's the same equation for pressure variation, just for the ideal gases within the troposphere region and within the earlier portion of the stratosphere region, based upon, since we know what is the temperature gradient within the troposphere region, and we know what is the that it is uniform temperature in the earlier stratosphere region. So we can develop the pressure variation equation. Now these two equations needed, if needed, in the formulation will be in the solving of numericals will be provided to you in the exam. So this equation will be provided to you in the exam, and this equation will be provided to you in the exam if needed. Okay, so we have a numerical here. This numerical is for the troposphere region. So we needed this formula. Okay, so within this formula, T naught, P naught, Z naught, these are all constant values. They are provided to you. This formula will be provided to you. Just the thing is that you have to just substitute the value of elevation, specific elevation that we have. And so we can just substitute the values and we can get what is the pressure at that elevation. Okay, so these are all the fixed values: Z naught, T naught, alpha, T naught, P naught. These are all the fixed values provided. The only thing that you have to put here is Z. Even the equation will be provided to you. Okay, and so you can find out what is the pressure. This is for the case when you are in the troposphere region. Okay, now if suppose you are in the stratosphere region, then this will be the equation. But again, the equation will be provided to you. Okay, so you have to just substitute the value of the elevation. Okay, and you can get what is the pressure. So these are the two very simple problems. Most probably will not come in the exam, but because in these problems, everything I have to provide except you have to just put the value of elevation. So hardly there is anything to judge. Okay. Anyways. Okay, now let's talk about pressure measurements. Barometer. Did you study barometer before? So do you understand the concept of barometer? First of all, barometer, why do we call barometer a barometer? No, the term means heat in Greek. Bar means pressure. So the instrument to measure the pressure is barometer. The instrument to measure the temperature is thermometer. We are using the Greek terms. Okay. So in Greek, for heat, it's thermometer. For pressure, it's bar, so barometer. Okay. Not because it's shaped like a bar. Okay, so the concept is that basically, if we take, let's say, if we take a tube, a small column and we fill it with mercury. Okay, then what we do is that we invert it in a container filled with mercury. So what will happen? The thing is that the mercury will try to go down into the container. But as the mercury will try to move down in the container, at the top air cannot come in because it's glass. The only way air can come in is if air can pass through the mercury in the container and then go into the tube. But the air does not do like this because air has very less density. Okay, it cannot penetrate through. Okay, and here we have glass, so air cannot directly enter. Now I have this glass column and I flipped it, or I turned it upside down. Mercury should fall down, and because of its weight, it will try to go down. Okay, so because of the weight of the mercury will try to go down. But what will happen is that because as the mercury starts going down, now I have vacuum here inside the glass. Okay, however, outside I have atmospheric pressure. So atmospheric pressure is going to push the mercury in the container down so that some of the mercury will enter back into the column. And now there is a tug of war. The weight wants the mercury to go down, but the pressure outside air, atmospheric pressure wants the mercury to go back up. Okay. And the level is going to be, it will be an equilibrium at a point when the two forces are equal. So the force of the weight of the mercury is equal to the atmospheric force, the force due to atmospheric pressure. Okay, when these two forces are equal, so that is the point when it will level. And through this, we actually determine that how much is the atmospheric pressure. Okay. So how much is this atmospheric pressure that can hold this much column length of mercury? Okay. Now, even here, our analysis would be similar. Now, look here. This is the point where I have, you can say, let me call this as the point where I have, or let me just name it as 1 point. Then this is the point, I will say 0.2. This is the point. This is the point, I will say 0.3. Okay. I know at 3 it is the atmospheric pressure. Okay. But I know that 3, 2, and 1 are all in the same fluid. So whatever be the pressure at 3 will be the same as pressure at 2 because it is on the horizontal line. Okay. Whatever the pressure at 3 will be the same as pressure 2, will be the same as pressure at 2. Okay. So P3 will be the same as P2. Okay. And P3 is atmospheric. And I know that P3 is basically P atmospheric. Okay. And from 2 to 1, if I'm moving from 2 to 1, so I'm moving up. Right. So if I start from 2, so P2, if I'm moving up, so it should be negative sign, minus gamma of mercury into height equals to P1. Now I don't want to write things in gauge values. I want to write things in absolute value. I know this is absolute 0 here. I'm saying that there is vacuum here, right? So P1 is 0, but this 0 is not gauge 0, it's absolute 0. There is vacuum, okay? So if I'm putting the absolute values, so I can find out, I can say that P2 is equals to gamma Hg into H, okay? Which is equals to, because P2 is equals to P3. which is equals to P3, which is equals to P atmosphere. So I can find out that what is the atmospheric pressure. So the atmospheric pressure is basically equals to gamma into H. And that will be the absolute value because I'm using here absolute. Since P1 was absolute, I placed it 0. Okay. So P2 becomes this, which is the same as P3, which is the same as P atmosphere. So I can get the value of P atmosphere. Okay. So practically when it is done, turns out that the height of the mercury column is about 760 millimeter Hg. Okay. So if I put here 760 millimeter and I put the value of gamma here, I will get the atmospheric pressure, which is the absolute. It doesn't matter. You always start from the point known. You always start from the point known. तो यहाँ पे basically known था 0.3, पर मैंने 3 को 2 के इक्वल किया क्योंकि वो सेम एलिवेशन पर है. फिर अब मुझे 3 पता था तो मुझे 2 पता है. अच्छा 3 मुझे क्यों पता है? Because 3 is the atmospheric. Okay. आप इसको other way around भी लेके जा सकते हैं. You can do it other way around. Let's say if I want to take it other way around, okay, then I'm moving from 1. Okay, so it will become P1 plus, now I'm moving down, so it should be plus gamma Hg into H. This thing will be equals to P2, right, which is equals to P3, which is equals to P atmosphere, right? This is the same thing. Here what is written is that I'm saying P1 is 0 vacuum, but here it is saying that no, some of the mercury will evaporate. Some of the mercury will evaporate. So there will still be some vapor. Actually, there is one concept that within this world, you cannot achieve vacuum. I mean, you can try to extract as much of air or as much of vapors from something, but something will evaporate. And there will be a little molecules, some of the molecules available there. You cannot achieve vacuum. Like you cannot achieve 0 Kelvin, you cannot achieve perfect vacuum in the world. Yeah, outside, naturally, outside the earth, if you go into the space, there is vacuum, but this is not something that you developed, it is naturally there. But within this atmosphere, you cannot achieve absolute vacuum. Okay. There will be small, very small amount of pressure, but it will be there. It's not possible to eliminate each and every molecule. So here they say that instead of saying P1 0, they say P1 is basically PV. But later on they say, okay, PV is considered 0, negligible, is not there. Okay, so this is Mercury Barometer because it uses mercury and used to measure the atmospheric pressure. Then we have an aneroid barometer. I want you to read it yourself. How does an aneroid barometer works? Again, its main objective is to measure the atmospheric pressure. Then we have other devices. Now these devices are not used to measure atmospheric pressure. Rather, these devices are used to measure gauge pressure. So these are the gauge pressure gauges. One is the Borden tube gauge. Within the Bourdon tube, what happened is that we have a tube, curved tube, and this curved tube is filled with the gas. Now, when I connect this curved tube with any other gas, having a certain pressure, so what will happen? It's going to pressurize the curved tube and try to reduce the curvature. Okay, so it is naturally curved, but when you pressurize it, it's trying to reduce the curvature. And with the change in the curvature, it is connected with the pointer. The pointer moves and it gives you the reading that how much pressure is of the gas which is connected to this Bourdon gauge. Okay, so that's basically a mechanical, but it's not very accurate. Okay. But it's low cost, reliable, reasonably accurate. Whenever I say reasonably accurate, it means it's not very accurate, but just you can on a reasonable scale. Okay, then we have manometry. Through manometry, we can actually determine the pressure. Okay. The most common and the most simplest device to measure the pressure is the piezometer. Piezometer is basically what? It is just a pipe, a tube, simple tube. Okay, and it is just connected in a pipe, or it is made to be connected to a pipe from which the fluid is flowing. So suppose I have a pipe here. This is the main pipe from which the fluid is flowing. I want to know what is the hydrostatic pressure. I want to know what is the hydrostatic pressure of the fluid flowing through this pipe. What I'm going to do is I'm going to make a small hole and connect this tube. What will happen? Whatever the fluid flowing through the pipe, some of it will enter into this tube. Okay. Now, the height to which the fluid enters into the tube, this height is going to determine the hydrostatic pressure. Okay. This height is going to determine the hydrostatic pressure of the fluid in the pipe. The larger the pressure, the more height it will go within the piezometer tube. So piezometer is basically simple tube, nothing else. एक आप ट्यूब ले लें, वो piezometer है. You connect it to anywhere where you have the fluid flowing, some of the fluid will enter into the piezometer. And now you can just check that what is the level of the fluid which enters into the piezometer. The level of the fluid in the piezometer is going to determine how much is the hydrostatic pressure inside the pipe. Okay. And how to calculate it? P equals to gamma h. Simple formula, P equals to gamma h. Gamma is the specific weight of the fluid flowing through the pipe. H is the height to which it enters into the piezometric tube. Okay. Now, piezometer is the simplest device to measure the hydrostatic pressure, but it has some limitations. The very first limitation is that the fluid must be liquid. अगर गैस होगी तो गैस तो piezometer ट्यूब से बाहर निकल आएगी. अब height कैसे find out करेंगे? First of all, it must be liquid. The fluid flowing through the main pipe should be a liquid. If it is not liquid, or if it is volatile, there are some liquids which evaporate on it their own. So even if it is volatile, then you cannot. So piezometer has a limitation. The second limitation is that suppose it is liquid, but the pressure is very high. So that means you need a very big piezometer tube. Otherwise, the water or whatever the fluid is going to go out of the piezometer tube. Okay. So for a very high pressurized pipe, okay, again, piezometer tube is not a good option. You need that much space, long. Okay. So these are the two major disadvantages because of which, yeah, it's the most simplest device, but cannot be used in many applications. Okay. Gamma is specific weight. Gamma is equals to rho g. Okay, the next device is a U-tube manometer. The next device is U-tube manometer. ये मैं बताऊंगा आपको कि क्या इससे रिलेटेड मैं क्या दे सकता हूँ. No, I never give MCQs. Okay, U-tube manometer. U-tube manometer eliminated one of the disadvantage. Okay, वो जो disadvantage था that we can only use it for liquid, cannot be used for the gas. Now U-tube manometer eliminated. Why? Because now we have a pipe, but I connect this pipe as in the form of a U shape. Okay, and within this U-shaped pipe, I put another liquid in it. So even if air is flowing through it, so air is going to come here, will push the liquid of the manometer, will push the manometer fluid, but will not going to come out. Okay, so it's trapped inside. Okay, so it eliminated the issue that you can. Okay, there was another issue in the piezometer. The other issue was that you can only determine the pressures greater than atmosphere. If the pressure was less than atmosphere, तो उस case में instead कि liquid goes into the piezometer tube, outside air is going to go and enter into the pipe. If the pressure in the pipe is less than atmosphere, instead of liquid entering into the tube, the outside air is going to enter into the pipe. So it becomes useless. Okay. So there were three disadvantages. What were the three disadvantages of piezometer? The first disadvantage, can only be used for liquids, not gases. The second disadvantage, the pressure should be reasonable. For very high pressure fluids, cannot be used because then the piezometer height should be very much big, not feasible. And the third advantage is that only for it can be used for the case where the pipe pressure is higher than atmospheric. If it is lower than atmosphere, then instead of fluid entering into the piezometer tube, it will be the outside air which will enter into the pipe. So again, useless. Okay, so this is the thing that I can ask. What is a piezometer tube? What are the limitations? And I have mentioned the three limitations. Okay. We had 25 minutes hand. Okay, U-tube manometer eliminated some of the disadvantages. Two disadvantages were eliminated. The first disadvantage or limitation was that lower pressures cannot be determined. Low vacuum pressures cannot be determined. Now vacuum pressure are possible to be determined. How? Because you see here, this is a U-tube. This is a U-tube manometer, and this U-tube is composed of a specific liquid, which manometer liquid, could be mercury, could be water, whatever the liquid. Now, one end is open to atmosphere. The other end is connected with the pipe. Okay. Now, if the pipe pressure is greater than atmosphere, what will happen? It will push the liquid level here down, and this level will go up. If the pipe pressure is lower than atmosphere, then the atmosphere will push this level down and this level will go up. So, but just by looking at the level between the two sides of the U-tube manometer, we can actually judge whether the pressure in the pipe is greater than atmosphere or smaller than atmosphere. Okay. So, whichever side is greater, that side level in the manometer, the liquid level in the manometer will go down. Whichever side pressure is greater, the other side level will go up. Is it clear? So this thing is now clear that now we can also judge how much, whether the pressure is gauge or vacuum. Wherever the pressure is higher, it will push the liquid and level down in the U-tube. The other side, automatically liquid level will go up. Now, how much is the difference in the pressure? How much higher or lower than atmosphere? It depends upon the difference in the level between the manometer. No, that's another thing. That's another phenomenon. Here, this YouTube manometer is just used to measure the pressure. This is a pressure measuring device. Whatever the difference between the two levels, just we measure how much is this height, multiply by gamma, that's the pressure difference. Okay, so the formula is again the same. P is equals to gamma H. Okay, so whatever the height, so that's a pressure difference. Multiply by gamma. अच्छा, इसको हम डायरेक्ट अप्रोच में देख लेते हैं. Okay, let's look at in direct approach. If I want to know how much is the pressure in the pipe, so this is P4, right? We are always going to start from the point where we know the pressure. So we know the pressure which is open to atmosphere, that is zero gauge. Okay, so if I write the equation, so P1 पर हमें पता है pressure. Okay, so we have P1. Now we are moving from 1 to 2. Okay, so but we are moving down. So P1 plus gamma of the manometer fluid, let's call it M, whatever the fluid here it is, gamma M into delta H. Let's say this is delta H. Okay, so now we have moved from point 1 to point 2. This thing is the same as point 3 because it's the same fluid, same manometer fluid. Okay, so whatever the pressure at 2 will be the same as pressure at 3. Okay, now from 3 onward I can move up to reach 4. Okay, so when I'm moving up, so it should be negative, because whenever you move down it's positive, whenever you have to move up it's negative. Gamma, now this gamma will be not for the manometer fluid but will be for the pipe fluid, because this pipe fluid has come to this point, right? Okay, so gamma, let me say here P, whatever P into L. This is L. Okay, sorry, no, P, gamma P is the gamma of the pipe fluid, multiply by L. This thing is equals to P4, right? Look at the equation here. P4 is equals to P1 plus gamma Hg, if it is said that here we have mercury, if gamma Hg into delta H minus gamma water, suppose here we have water, into L. I have written it in the general form like this. P1 plus gamma M. M means mercury, manometer fluid. It could be mercury, it could be whatever it is. Okay, into delta H minus gamma of the pipe fluid. Pipe fluid could be water, could be air, whatever it is, into L equals to P4. So what I've done is that I started from this point for which I know the pressure, because this is 0. It's open to atmosphere is 0. And then from this point onward, I have determined the pressure in the pipe. This, what I have written here directly, is done in multiple steps and shown here in this formula. Is it clear? But the direct approach is something that you can apply anywhere. So far, it's clear? आज के लिए मैंने सोचा हुआ तो था स्लाइड नंबर 45 तक, 45 तक तो मेरे ख्याल से मुश्किल है। हाँ, कोई बात नहीं, आप तो क्लास में बैठे, घर जाने की जरूरत नहीं, बैठ के पढ़ाई करो। Okay, now this is one problem. This is related with the formula shown here. Okay. For YouTube manometer, water at 10 degrees centigrade is the fluid in pipe. Here it is said that water is in pipe, and mercury is the manometer fluid. Okay. If the deflection delta H is 60 centimeter and L is 180 centimeter. Okay, so here it is given the value of delta H and L. Okay. What is the gauge pressure at the center of the pipe? So we need to know what is the gauge pressure at the center of the pipe. Pipe means P4. We need to find what is P4. So here in this question, delta H is given, L is given, P1 is 0. And we know that the manometer fluid is mercury, and we know that the pipe fluid is water. So we know the gamma of water, and we know the gamma of mercury. So I don't need to solve it because it's the same formula, just substitute the values and you're going to get the answer. So the P4 comes out to be 62.1 kilopascal gauge. Okay, let's see this problem and we are going to end after this problem. Okay. What is the pressure of the air in the tank if L1 is 40 centimeter, L2 is 100 centimeter, L3 is 87 centimeter? So see the connection here, see the diagram. We have this container filled with oil. At the top, I have air. Okay. Then obviously the oil enters into the pipe till this point. After that, I have again air. Then this is connected with another pipe, mercury. Here we have mercury. And then this is open to atmosphere. So what I need to find, what is the pressure of the air in the tank? So pressure of the air in the tank. So I need to find the pressure here. This is what I need to find, first of all. Do you understand what is asked in the question? Okay. Now, in order to solve it, as I always tell you, by direct approach, always start from the point for which you know the pressure. So here, point 1 is the point for which I know the pressure directly. Okay. So I will start from point 1. Okay. So P1. Okay. Now from point 1, I will move down. How much I will move down? L3. Okay. Until I reach at this point. Okay. So it will be P1 plus, because I'm moving down, gamma of mercury, gamma of Hg into L3, right? Now I have reached this point. Since the pressure is same in the horizontal level, so I will jump from here to here, right? Then now from here, I will move up. So it should be minus. Okay. So minus gamma of, this is air. Okay. So minus gamma of air into L2. Right. So now I have reached from this point till here. Okay. Now, since within a fluid, the level remains at the same level, the pressure is same. So I've jumped from here to here. Okay. So now I will move down. Okay. But how much? I don't want to go overall down. I just want to know the pressure here. So whatever the pressure here will be the same as pressure here, because it is the same fluid, oil, at the horizontal level. So I will just go down this much. Okay. So further going down, so plus, when I'm going down, so it is now the oil. So gamma of oil into L1. This thing is equals to pressure here. So that's P air, or I will say P2 here, because it's mentioned 2, so P2. Is it clear? Now here, one thing that point to be noted is that P1 is 0, because it's starting from 0, because we are talking about the gauge pressure, right? And so P1 is open to atmosphere. So P1 is 0, right? So gamma Hg will be known. The question normally it is given. Okay, for example here, because gamma Hg, इसकी specific gravity होती है 13.3 around something. Okay. So आपको provided होगा कि specific gravity क्या, based on the specific gravity you can find out what is the gamma. Formula क्या है? If you know the specific gravity is equals to gamma of any fluid divided by gamma of water. Gamma of water is 9810. That I have told you that you should memorize it. So if the specific gravity of mercury is given, you can find out what is the gamma of mercury, right? So this for this oil, the specific gravity is already given, 0.8. The diagram may be given. Okay. So L3 is known. Okay. Now there's one point to be noted is that I'm saying that whatever the pressure here the pressure will drop as I move up, but this is air, and I told you that the hydrostatic pressure variation with elevation is applicable for the case of liquids, but for the gas we ignore it because it is very small. Actually, अगर gamma air की value पता है आपको, अगर given in the question, you can use that. That is also okay. But even if you use it, you will realize that the gamma is so small for the case of air that this term is almost negligible. You can, in reality, ignore this term. You can ignore this term. So the equation would still be valid because the gamma air will be very, very small. Because gamma is rho g, and rho for water is 1000, for air is 1000 times less. Okay, so if the rho is 1000 times less, that means gamma is also 1000 times less. So in reality, it's not going to affect much. Okay. So you see here, where we have gamma air into L2, it is directly placed as 0 value. Okay. Just ignored it. Gamma air was not provided in the question. But when you are ignoring it, you have to give the reason why you are ignoring it. Because it is a gas, and for the gases, okay, this pressure variation with elevation is not applicable since the gamma values of gases is very, very, very small compared to that of the liquids. Okay. So you will ignore it, you will put the value 0, but in that case in the exam I need the reason why you have done it. Okay, so since you see here in the red, the reason is given. Since gamma liquid is very, very big compared to the gamma of gas, or you can say gamma of gas is very small compared to that of the gamma of liquid, it is well within engineering accuracy to neglect changes in pressure due to gases. So that's why this term has been cancelled. Okay. The other thing is Other things are simple. You just substitute the values, solve, and get the answer. So we finish our lecture today at slide number 33. Inshallah, from slide number 34 onward, we are going to start in the next class. The Monday's quiz already mentioned कर दिया है कि वो ये lecture involve नहीं होगा. हाँ, you can say that chapter 1 and 2. Lecture 2 and 3 में chapter 2 है. Lecture 1 तो पहले ही नहीं, chapter 2 and 3 में chapter 2 है. chapter 2 till lecture 3 है. मतलब बेसिकली जो पहली 2 स्लाइड्स है ना आपके पास, वो है वो कवर करना. मिड्स में इस स्लाइड तक आएगा, मींस लेक्चर वीक 4 and 5 till लेक्चर वीक 5 मिड्स में आएगा. As I told you, पेपर अभी डिस्कस नहीं किया है, मैंने भी बनाया भी नहीं है, but as a general rule, you will have numericals 70% or more, and you will have conceptual question, theoretical 30% or less. Yeah, reasoning. अच्छा, कोई भी conceptual question उससे बाहर नहीं होगा जो मैं बता चुका हूँ आपको. जो भी lectures में I have mentioned कि तो चीज मैंने बताई थी कि you have to memorize this definition, or this derivation can come, or this thing I can ask, or that thing I can ask. Whatever I have told you in the lecture, okay? उससे बाहर नहीं होगा. MCQs तो बिल्कुल नहीं. No. So conceptual questions where you will be asked some reasoning or numericals. But numericals में भी दो चीजों का ध्यान रखना है. अगर कहीं पे reasoning है, you have to get the reason. For example, in this question, you're putting a 0 here, there should be a reasoning here. Okay, so wherever there is a reasoning needed, that reasoning should be there. Number one thing. Number second thing is that units. You don't have, you make sure that you do not make mistake in the units. Either you don't miss the units or you don't write the wrong unit. Okay, because units, जहाँ units आएंगे वहाँ 0.5 mark is for the unit. You know, the 15 जगह units आ रहे हैं तो 7.5 number units में जाएंगे. ठीक है? So you don't mess up in the units. Okay. The other thing is that yes, there are homework problems. Homeworks for problems for chapter number 1, homework problems for chapter number 2, and homework problems for chapter number 3, because this is chapter number 3 till lecture 5, lecture week 5. So they're already uploaded. The lecture slides, at the back of the slides you have the homework problems, and yes, और book भी आपके पास uploaded है. ठीक है? So you have to cover that. So अगर let's say if I am making an exam of 20 marks, जो कि 20 marks का होगा, तो उसमें से at least 5 marks will be from homework, and 5 marks will be from homework, 15 marks will be from lecture. So you have to cover that as well. Okay, so far course heavy है, speed बहुत तेज है, but these are not a matter of concern for me. Matter of concern मेरे लिए ये है कि if I'm going fast enough that you are not able to pick up, आपको समझ नहीं आ पा रहा है course, then this is an issue. Are you able to understand the material, what I'm going through? ठीक है, ज़्यादा है वो, that's another issue. ठीक है, रफ्तार भी तेज है वो भी another issue, but it's okay. ठीक है, but चीज़ है कि समझ आनी चाहिए, समझ आ रही है तो ठीक है, फिर मेरे लिए खैर है, आप लोग जाने. If there is a topic which I have gone through and you feel like you do not understand, you can let me know, we will cover it again. Okay? But the speed will be a bit fast. Okay, that's it for today. You can leave.